Okay, we're back. I'm going to share this and we'll get started. Actually, wait. Almost there. Okay, now we're live and get started in 5 seconds. Have to wait for Twitter to generate the view preview. Okay, so Jim Keller is one of my favorite engineers now, and he designs computer chips. And I'm a mechanical engineer. I don't know anything about computer chips, but the way he speaks about them is fascinating. Um, and more relevant is the way he speaks about the philosophy of engineering is really fascinating. And if you get a chance, I would highly recommend you listen to his two interviews with Lex Friedman, and any interviews really, but his two interviews with Lex specifically are fascinating. But he talks about how he solves problems. And by the way, this is all going to circle back to welds here in a second. He talks about how he solves problems. And one of the ways he does this is he will think deeply about a problem and then go to bed. And he says that when he does that, he will actually either dream about the problem or he will wake up the next day with the solution. I would like to say that I woke up with the solution to this weld problem. The answer is I didn't. In reality, what happened was I woke up, was still frustrated by it, and then sat down and forced myself to think about this for 2 minutes, and then I think I came up with a solution. But I think part of the reason I was able to do that was by just sleeping on it. Sleeping on it really does fix things. So anyways, let me describe the let me describe what we're doing. Let me describe the problem, and then I will tell you what the solution, I think the solution will be. We're going to find out on the stream if this really is the solution. So the problem was we were analyzing this frame and we were applying a load P here. And we want to find out, well, actually, first, what are we doing? We are designing a modular framing system, much like Mod Truss, much like Unistrut, and much like 8020. We are going to make a modular framing system. Why is this significant? Well, because we're going to open source it. It's also significant because it will be super accurate because it's going to be using a laser cutting process on standardized tubing. It'll also be valuable because I'm going to open source all of the calculations and give tools to engineers to use this stuff for things like tooling framing or whatever their heart's content is. That's why this is valuable. The team at FabWorks came up with an interesting way to terminate quickly a tube into another tube for this modular framing system. That's the thing we're working on right now, is how do you build this into a standardized part library and a standardized analysis library that engineers can use to quickly fabricate, without welding, framing systems that they can use for building out machinery, prototyping, anything like that. That's what we're doing. What was the thing yesterday that got me confused? I was doing this weld analysis, and we got to the point where we found the reaction loads at the weld, we solved for them, and we realized that the reaction loads were dependent on force. But we're trying to find what force the frame is capable of withstanding. So that is where I got hung up yesterday. So I slept on it, like I said. And I think I have the solution to this problem. The problem was my thinking around this was wrong, and the math is right. To state this again, we're trying to find the maximum load, P, that the system is capable of withstanding and what we're considering the most conservative loading case, or the loading case most likely to destroy our frame. We're looking for P, and I solved for R. You see where I'm going for this? Well, what we should do is solve for P, which is what the load is capable, or what the frame is capable of supporting in terms of load, and then plug that equation for P into our weld calcs down here. So really, this problem goes away, and I wasted 12 hours because of this line right here. When you do this, it all goes away, right? Because now we have we have P described. We have our reaction forces. Now we don't know what the reaction forces are yet. We're going to find some way to substitute them in, and we're going to solve for this. I think that's how we're going to do this. Yes, that's right. Or the other way around. We leave it as it was, and we solve for P here. Yeah, that's right, actually. Sorry. So you solve for P here, and then you get your answer. So then we plug that into this equation, and then we find out what our actual P is. Okay, are you following along now? And in reality, this isn't P, this is actually R. Well, let's leave it as P for now. And we will bring this over to simplify what we're trying to do here. So this is the stress, right? This is our shear stress. This is the stress as a function of the load applied, P here, and the variables that determine the stress in this weld. So we actually know tau, or shear stress. So that's what's going to give us our pseudo P here, which is not really P, it's the reaction forces. And then once we get the reaction forces, we can solve for P. So I just talked a lot, and I didn't really do enough drawing. So I'm going to do that, and we will hopefully make some more sense of this, and we can get back to work, because this really held me up yesterday. Okay, so to restate, we want what is the maximum load the frame can take? So let's find that out. Let's solve these equations. Equation 1 and equation 2. And 1. So we have shear stress is equal to the reaction force, or P, but in our case, the reaction force. So we're actually going to switch out P for the reaction force. So that becomes R1 or R2, but they're equal. So we're just going to call it R sub 1 sub 2, because we've been using that nomenclature so far. The beam will bend, Levi. The beam will bend. We went into it yesterday, but essentially this is what's gonna happen. This beam is going to deflect. It's going to deflect delta max, and we can calculate that. So that's going to happen regardless. But at the same time, you're resisting the moment generated by that load. And you can see here the maximum moment is at the center and at the ends. And so what we're talking about is at the ends we have this weld that has to react this load, or this moment specifically. That's what we're working on right now. So yes, we do want the beam to bend. It will bend. We have to manage that bending at the ends. So let's rewrite this equation as I've just done, and that's going to be 0.707 times h, which is the length of the weld, times L for the length of the weld. So now this is equation 3. We're getting there. We now pull from equation 1, and we'll just actually copy that over. And this was equation 1, right? Yeah, this was equation 1. So we want P, so we've solved for P now. And when we do that, we get R sub 1, 2, 4 times that, because we're pulling this up, times W, which is what was W? It's the width. Yeah, the width of the tube. And that's divided by L, the length of the weld. And that's equal to P now. And so here's equation 4. So now you can see where we're going with this. We have shear stress describing the reaction, and we have P, which we want, and that has the reaction. So if we solve for the reaction now, we can actually plug 3 into 4, and we can actually find out what our maximum load the frame can withstand is. So we're going to do the same thing. We're going to move these terms around and solve for the reaction load so we can plug it into this equation. And so what happens? We get 0.707 times, and again, we're pulling all this up, times H times L. And that is equal to R sub 1, 2. And this will become equation 5. And so now we get our solution. So we sub 5 into 4, and we get P, or the load. So now we do that. So we'll take, so we're going to write out 4 until we get to the reaction loads, and then we'll substitute this equation. So we get 4 times, and now we substitute equation 5 in, because we're saying this is equal to this, and we have this, so we can actually substitute this in. This happens all the time in engineering. It's a great way to define theoretical maximums for things. And so now we're going to do that. So we get 4 times 0.707 times H times L. And what this equation is essentially saying is, here's the strength of the weld. And now we get the factor for the moment decoupling between the two reaction loads acting on the welds. That's right here. And so W is this width. And then we divide by L, and that is equal to P. And that, ladies and gentlemen, is how we find the theoretical maximum load that our frame can take. Asterisk, an eagle-eye viewer pointed out that there might be a design fault in the tabs, and we're going to address that later. But for now, we focus on welds, and we focus on theoretical maximum load capacity, and we will figure out the rest of the design. That's how this works, sometimes. Okay, so here's our fancy equation. We politely ask the chat GPTs to solve it, not solve it, to write it on LaTeX so we can solve it. And then we go find out how much load we can take. Very exciting. So let me move this around so it makes more sense. Okay. So let's double check this. Make this markdown. Why did you go away? There we go. 4707 HLW. 4707 HLW divided by L. Love it. Okay. So let's go back to our egregious and incorrect version of the calculations yesterday. Weld coefficient. I'm glad you brought that up. We're about to get to one of the most interesting reasons why you rarely see welded aluminum in high capacity applications. And it's not just because it's hard to do, it's difficult to do good aluminum welding. That 0.7 you're talking about is the knockdown factor for the heat affected zone, and we're going to talk about that for sure. So yes, we will add that coefficient. And we're going to have to dig fairly deep into the ADM, or the Aluminum Design Manual, to find that value. The reason that happens is because when you weld, you take the aluminum past its, I want to say its critical temperature for that temper, but I don't know what the technical term for it is. Essentially, you turn it from a nice tempered aluminum into a gummy, weak, non-tempered version of it. And tempering is a large part of why aluminum is can be strong. And that's the factor I think you're talking about. But we will do that. That's right. Okay, so let's clean up this potential nonsense, and then we'll get to the solution here. This will be fun because we're actually going to get a number out that says you can hold X number of pounds, which is very useful for comparison to design alternatives, like the tab and slot detail we're about to talk about. So we said the weld stress, the shear stress in a weld is this, which is true. The welds are counteract the moment. We might want to clean this up though. Peel over 4, and then we solve for R, which is what we wanted to do. That's good. So actually we leave this alone. So denominate a word. Yes, so. Can you see this? You can probably see that. Oh, this is that's the GitHub. That's gonna get confusing. Take this to another page. By the way, all of this work is going to GitHub. So if you'd like to check the work, if you'd like to use this, if you'd like to do anything with this repo, feel free. It's at my GitHub. But if you just Google, actually, if you go to tinyframe.dev, I think it takes you there. I think it does, yeah. Go to tinyframe.dev if you would like access to all of this. Okay. Name the reaction load. this. We substitute R into F for the fillet weld equations and solve for P, simplifying to. There we go. Now we get to do the math. So the number of welds we actually should we substitute that in? We should actually build that into the equations because we used 2 over here. Yeah. So that actually becomes NW. So it becomes N times W over 2. So N over 2 sits next to W. We can just quickly put that back in. N over 2. Where's my W? Right here. So it's actually N over W. Is that right? Yes, because it's symmetric. It's not rectangular, it's a square cross section. So we'll add the N and then the 2 there. Why is this hard to... Oh, it's omega, that's why. So there's 2, and actually we bring that over because we have 4 here. So we just make that 8. Right? Double check that. Yep. Oh, but we have that 8. Yeah, so that, okay. That cancels out. So this actually goes back to 4. Right? This is, yeah, so for us, this becomes 2, right? Let me just write this out. So we have 2, wait, let me, N over 2, okay, let's just solve for this and we'll make it make sense again. Okay, so 4 over 2, that makes this 2. Okay, we're there. So we want 2 and then N. I forgot to get N. That's okay. Add it back. We'll write these out. N is the number of welds. H is the size of the weld. We should actually denote this H weld because we have H declared elsewhere. HL is the length of the weld. Okay. This is redundant. Oh God, I hate when it does that. Okay, and then we have L, we set N. W is the width of the tube. I gotta learn how to do new line in Markdown. BR, yeah, I'm not gonna do that. 2 spaces. Well, that's why that wasn't working. Okay. That's all explained. Now we can declare this and then get to work. Actually, let's bring in the equation too. Gonna replace omega there. So P is equal to, so it'll actually be P max. Does W, I think we call it T width here. Yeah, T width. The length of the tube. Okay, and then this justification is, yeah, we're redeclaring the variable W as variable T width of the tube as W for legibility with the equations. Okay, so this solved. That's good. We print this out and see what the solution is. Let's actually see if I can remember how to print out two decimal places for a float. Oh, we forgot to include tau. Where did tau go? I messed something up here. Let's equal P. Oh, tau is supposed to go in here. Duh. Times tau. Yep. Messed that up. It's okay, we caught it. And then that goes here. So 2 times tau. Tau is the shear stress. So walking through this again, tau, we bring all this up. We get R. We place R into this. So yeah, tau actually went here. Okay, so we'll just insert tau into those equations over there. Four times tau clean this up too. Okay, looking good. And so we have to declare tau yield as well. And we do these declarations up top, so maybe we should do it up here. We're going to have to do a trick. So the yield stress for a ductile material is actually different in shear than it is in normal loading. And I believe off the top of my head, so in other words, what that's saying is when you load a specimen, if you load it in shear, you actually get less strength than if you were to just pull on it. And it is roughly, and we're going to go double check this, but I think it's roughly 0.61 times your yield stress. And we will double check that. So conservatively, you can use half, but really it's I think it's 0.61 or 0.62. Okay, so I'm trying to find the citation on this. They have it as dividing by 2. So this is, my AI is not going to replace my job just yet because I don't think this is even really on the internet in a meaningful way that AI would pick up and know how to use meaningfully. But we'll test it out. I believe it's 0.577. Yeah, this is in Shigley somewhere. Yeah, so 0.577. So that's a knockdown effect. Okay, and that's independent of the one we're about to do for welding. Uh, yeah, Python with Pint has been a great analysis workflow. The it isn't particularly strong when it comes to usability day to day. As you can see, a lot of work is done by LaTeXification of my equations with ChatGPT. Like 4 years ago, this would have been very useful because I have to write out all the LaTeX manually. Um, Another one that I like is Quarka, which is promising to be really good, but it doesn't have evaluation yet. So in other words, you write out essentially this is going to replace, this is going to be the de facto analysis tool for engineers, I think, in 10 years. Um, Pretty sure. If they can build out the evaluation, um, and they can build out essentially integration with Python and MATLAB, essentially if they expose an API, this will be the de facto. It's MathCAD that doesn't suck, as far as I can tell right now. So this will be in the future very good. Right now, I've chatted with them a little bit and they don't have evaluation yet. That's really the limiting factor. So once they get evaluation, this will replace Python and LaTeX for me. Um, yeah. The fun part is when you take this Python code and you start to plug it into your CAD. Um, yeah. Or will you plug your CAD into Python? Who knows? What is the future going to be like? What is the future going to be like? The only way to know is to build it. So let's do that right now. Let's get back to building. All right, I think it was %2f. Something is telling me this isn't right though. There's no open source version of MathCAD that I can tell. The open source version of MathCAD is essentially uh, Jupyter, which is this, with Pint. For my purposes, it works pretty well. CADWolf is not open source. SMath, I looked into it. That's also not open source. So this is the all open source version. What does ChatGPT say? What is an open source alternative to MathCAD? SageMath. I'm wrong. There is a version. What? On top of NumPy, SciPy, Matplotlib, SymPy. What? And R? Is this real? Define a function, yada, 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 but it's still a language. So if you're going to do a language, if you're going to use a language, the thing is, MathCAD isn't a language. Yeah, I think it has a language in the back end, but um, yeah, maybe SMath was open source. I don't think it is. Looks looks like it's not open source. No, this isn't it. Yeah, I want to be wrong here. So if you find something that is a non-programming interface version of Jupyter, essentially if it's MathCAD, but runs on Python, then the thing is like this would be a great business idea, except I don't. I mean, it's hard to monetize open source. Don't I know it? Don't I know it? Is there an alternative? Caveats. It's saying SMath. It's freeware, but it's not open source. Yeah, it's unintegrated like Kafka. Yeah, that's no. You're not sidetracking. One of the reasons why, actually, the main reason I'm doing these streams is because I wish someone was doing this when I was earlier in my career. The second reason is because I learn more from you a lot of times. I learn more from you. And so this example is perfect where you're showing me that actually S math might actually be an alternative. So for instance, Pint, I learned about that from someone talking to me in one of my open source hardware channels in Discord. They mentioned that Pint manipulation was possible. Pint unit manipulation was possible in Python. So yeah, Sage Math. Maybe someone should take a look at this. Tutorial for beginners. It's still programming though, so it's still programming. We don't want a programming interface necessarily. Well, not necessarily. We definitely don't want a programming interface. Okay. So speaking of learning, I didn't realize, I totally forgot that the reason why the the reason why the knockdown on shear stress is not an intrinsic material property, it's an analysis thing where when you calculate the von Mises stress, you are doing some um, replacement of the stress along its um, I don't know what you call it, planes, and it's just a mathematical thing that spits out what you're analyzing for shear in some combined load state. So yeah, this is just Python. I mean, this is Jupyter as far as I'm concerned. So we already have a working open source version of this, which is Jupyter. I mean, this does look like Python, which is nice, but I really like Jupyter. So I don't really like Jupyter. I tolerate Jupyter. But fun fact: I actually tried to talk to the one of the creators of Jupyter because I was working at Amazon at the time, and he happened to be working at Amazon, and so I sent him a friendly little message like something like, "Hey, I actually use Jupyter. It's great. Love the work you did. Do you mind if I, set up a 15-minute coffee chat? I'd love to talk to you about, your path or whatever." Sorry, dog. And he told me to go fuck myself. He didn't say fuck. He said, I don't know, he said something like very, I forget what it was, but it was very, what's the word I would use? Ju Juvenile. Something very juvenile. And he was a lot older than me, which was super surprising. But if you ever know more than other people, and they ask you to help them know more, and they're genuinely interested in knowing more, you should probably talk to them. So, actually, he was the creator of IPython. So I actually don't use his software. I use it by accident or proxy through Jupyter. But yeah, that's actually, I staunchly believe this. If you are an engineer, it is part of your job as an engineer, regardless of what you do day to day, to grow and educate junior engineers. That's part of the job, period. Doesn't matter if you like people or not. Even George Hotz, the GOAT, the great, even he takes time to stream to show people how to be the best at his art. So if you ever find yourself getting short or angry with junior engineers, you should be very careful as to you should be very careful about that because we were all junior engineers and we all sucked at one point. And the only reason we're like the only reason I'm even able to do these calculations right now is I remember it vividly. I remember I sent a message to a senior engineer and was like, "Hey, I don't know how to do weld calcs." He's like, "Actually, okay, come in 30 minutes early tomorrow and I'll show you how to do it." And I still remember the whiteboard like it's in front of me. And he was like, "All right, here's the load." He actually drew this out. That's why I draw this section the way I do. He's like, "All right, you see this little throat? That's your T. You want that. That's your new A." And it immediately clicked, and he ran through it with me, and it was great. That it's funny, like most of what I know, I can think back directly to the engineer who taught it to me. Anyways, all right, that's a lot of digression. Back to calcs. So how do you actually? I keep asking ChatGPT how to do this. How do you print two decimal places in a variable? Python. I think I just forgot to declare the variable here. Um, okay, yeah, we forgot to declare the variable. We're getting close though. It's starting to look like this. 0.2f. Where was the percentage there? There's no percentage. I made that up. Pmax. Invalid decimal literal value. Oh, it has to be within. The saga continues. The saga continues. F. Are we having fun yet? Okay. Okay. So this is a load. It should be in pounds force or newtons. And we're getting KSI by distance, which means we're missing something here. And it's just it's just we forgot to attach a unit to one of these variables. So let's go find that. Tau yield, let's check that. Can you have two windows open of the same Python script? Not reliably. Okay. So let's just go through all of these and make sure that the units are correctly assigned. So KSI, tau yield carries over that unit. So we're good. So tau has it. Actually, you know what? A really ugly way to do this, but faster than scrolling back up and down, is going to be to just print all of these. So tau yield, H, print L. Oh, L cancels out. Why didn't I catch that? Aha, 50.8. That should have units assigned to it. So it's, where do we declare this? T-width. T-width is the culprit. T-width. No, wait, we assign it right here. So what happened? Does it lose its assignment? No. Oh yeah. Okay, we band-aided this earlier. T-width should get the unit assignment up here. And we clean this. So let's actually run all cells. Make sure it doesn't break anything. And it does, because why wouldn't it? This is Python after all. I'm not complaining about Python. I'm complaining that the state of the world right now is that the only really good way I can do calculations is using programming languages when I'm a mechanical engineer. So we grew some of our units here by doing this. Why does that not like this? Do you lose the unit association or something? Um, yeah, Jupyter, this is IPython, kernel slash whatever the software engineers call it. but it's a Jupyter front end. I don't know if it's effectively a Jupyter front end, but you can think of it that way. So why did that break? Let's see if this continues to break. This continues to break. Not just that, everything's breaking now. Okay, we're going to restart this. Run all cells. We might actually restart the kernel too. We'll find where this breaks. So it's in units here on FOS install, so sigma bending. Force pound millimeter, blah, 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 blah. All right, so I don't know why that broke. Sigma yield over sigma bending. Sigma bending is this. Hi, Peter. What happens here? So that's wrong. So this should fix. Okay, that fixes. I think it's fixed. So we're just gonna have to manually apply units here, which I don't like, but and this should fix now. Almost. So we're still getting stress times, I mean, this is annoying. So we're getting a value that's real. It's saying KSI in millimeter. So essentially we have load per millimeter squared, and this is canceling out with the millimeter squared, so it's just not converting. I don't know why it's doing that. Can we call the to function? Yes. Okay. Wow. 15,000 pounds. Oh, we forgot to account for the knockdown effect. So this is actually going to be half. I also doubt this. 15,000 pounds is a lot for a 2x2 tube. Yeah, it's a lot. I actually don't believe this calc. So we have to bring the knockdown into effect. But before we do that, let me explain what's going on. So we've been talking about this weld here, right? Well, something interesting happens when you weld aluminum. So when you weld aluminum, you first lay your first dimes, and this region here is really hot. It's hot enough to melt the aluminum, obviously, and the filler. But then that heat permeates as you continue to go along the length of the weld. And eventually, it heats up to a point where everything in this threshold at this line has been affected by what's called the heat affected zone. And a lot of you already know this. So it's very popular on YouTube to talk about how if you have really hard steel and you're trying to form it, or you have a hard metal and you're trying to form it, you blast it with a torch with a Sharpie on it. And once the Sharpie evaporates away, it's hot enough that you know that you've annealed the material. It's very similar to this, except we're not just, well, it is this actually. We're annealing the material. And so what happens is it ends at some point, typically here, and it depends on the thickness of the weld and yada yada yada, but um, or the weld size, I should say. But essentially, what happens is if you were to apply load to this now to break it, it's not going to break here. It's actually going to break right here, right outside of the weld, because it's the thinnest section typically, and it well, it depends. I shouldn't say that this is true. It depends on the geometry, it depends on the material and everything, but it's a case that this will actually happen. You'll break it outside of the weld. And so what happens is you get this heat affected zone, and what it does is it it takes your yield stress. So for 60, 61, um, T6, your yield stress is roughly 38 KSI. Now here's where it gets funky. You have a knockdown effect because of this heat affected zone. And so that comes down. And so just going off the top of my head, plus HAZ, you get some other value. And I remember, I think it was more than half. I think HAZ affected aluminum is like 9 KSI. I think it can be low. No, maybe 18. I think it was 18. We're going to go look this up. And then you have the fact that you're taking shear and you get half of that. Oh, that's right. And then you get 9 KSI. So your super skookum 40 KSI aluminum, which is roughly the strength of most mild steels at least, just turned into gum, useless gum because you welded it. By the way, if you look around the world, you'll start to see bolted aluminum frames for this specific reason. Because counterintuitively, you actually get stronger frames when you bolt them versus weld them because you don't get this heat affected zone. And so I'm going to stop talking for a second and I want to actually go find out what the HAZ effect is. We might have to pull up the ADM to actually take a look at this, but um, the rule of thumb I've used in the past is like a couple inches or an inch at least away from the weld itself. So let's find out yield. So actually what happens is they actually give you the values. You don't have a knockdown effect. Yeah, here you go. Look at this. So for, let's find 6061 T6. They're being liberal here with the value. They're saying 45 KSI, not 38, but the low end is 38. You actually almost half it. So as welded, you go from 45 to 27, which means you just knock down nearly 50% of your yield. And this, ladies and gentlemen, is why you don't want to weld aluminum. Besides the fact it's difficult to do, you lose a lot of your, your strength. So what we're going to do is we're actually going to create a as welded version here. So we have 27 KSI. We'll actually add that. So we have sigma yield, and then we'll have sigma yield welded, and that is going to be 27, and I think they said this was 45. Valid syntax, of course. Hits keep coming. You can tell I love software engineering because I complain about it all the time. Actually, that might actually mean I do love software engineering. Okay. So now we're going to change the tau yield to tau yield welded. We're going to change this to be factor of the the welded version. And we'll come down here and change these equations for that. I kind of want to find the, there we go, 5,000 pounds. That's starting to look more reasonable. I actually want to find the ADM source on this. If you are welding aluminum, I highly recommend you pick yourself up a copy of the aluminum design manual, especially if work's going to pay for it. Actually, I'm not recommending you do, I'm saying you have to. You should not be analyzing welds for aluminum frames if you don't have a copy of this laying around. So this is the actual rundown of this. Typically extends 1 inch, like I said, from the center line of the weld. Um, D 1.2. Yep, yep. But the good news is I believe you can post-treat your frames, but the problem is you have to take your giant frame and post-treat it, which is oftentimes unfeasible. And so this is the ADM, an old version from 1967. But we don't care. What we do care about is it searchable? It kind of is. Minimum for welded parts, 7.1, page 53. We're going to page 53. God, I love this book. I actually lost mine, so I might have to go buy one. I haven't welded aluminum frames in a while. Allowable stresses for welded parts. Nice, you can actually see the distribution as a function of distance from the weld. It's very cool. And is this a unit chart? Like, is this one here? That's pretty cool. Wish they gave us the Y values. Um, Man, they've got all the calcs for this too. This is fantastic. Oh, yeah, this is good stuff. I recommend picking up a copy of this. Okay, back to it. So we're saying 5,000 pounds. Does that actually make sense? Um, I don't know if I can link it. I think that might actually get me in trouble. So you should Google. What did I Google for? What did I do for Google here? I Googled aluminum design manual HAZ and ended up with this hyperlink. But I don't know if this is a legal copy, and so, you know, make sure it's a legal copy. Okay. So there's our fancy equation. There's our fancy answer. Does 5,000 pounds make sense? So we have a 2 by 2. I mean, let's just calculate the bending stress. I mean, the bending stress is going to be a good indicator. It's funny, actually. I think the tube is going to fail before the weld does. Yeah. So, yeah, we can figure that out right now. So this is a 2 by 2. All right, so remember, so we have P, which is P max. Remember, bending stress is sigma B test is equal to Sigma or bending stress is equal to MC over I. So where do we declare C? Yep, we got C there. That works. Um, H, yep, that's right. Moment. Oh, wait, that's right. Um, we actually have moment. It is P times L over 2. So we're going to place this. P times L over 2. And P is P max, like we talked about. It's L over 2. Actually, no, remember um, we used this. So our bending max is actually, our moment is this value, PL over 8. I'm sorry, because it's not a simple cantilever. So PL over 8. And where do we put our L? I want to make sure that we're using the right L. L got canceled out. Actually, just so we're not confused, I should change this to L sub weld. Okay, and I'm going to change it in here too. So keep looking for L and L's length there. So L weld, PL over 4, this is the length of that lever. Okay, that we might have made a mistake here, and that's why that value might seem a little high. Because we were confused. We were conflating L, the length of this beam, and L is in the length of the weld, so that might have been a problem. So we'll double check our work here. So PL over 4, this was the right L. This is the length of the member. And this is where we introduce, okay, yep. So we did do this wrong, and we're going to fix it right now. So this one is not L weld, it's L. And that should error out. It doesn't error out. Why? Oh, because L got defined elsewhere and we redefined it. So we have to go back and find the original L. Determine the length of the tab. Okay, well, yeah. This is all very wrong. Okay, so we have to put in the length. L equals, all right, we're gonna do L sub length of the beam. And that is this distance, which is 898.4. Okay, this should change our variables, or our values, and it doesn't because we haven't changed this yet. There we go. Now this number makes more sense. 300 pounds. That seems reasonable. So in other words, if I have a super big lunch and then I stand on this beam, it'll barely hold me. I believe that. Way more than I believed 15,000 pounds, which is the one we started with earlier. So 300 pounds. And that's welded. That's welded. And so you might ask, well, what if we can get 4 welds on this thing? This number should go up. It doesn't go up. Why didn't you go up? Because we forgot to include the number of welds. Look at that. Let's double check this. Number of welds was next to the width. Okay. Times n welds. Okay, so that goes up. And if we bring this down, it goes back down. All right, so that was the number it could withstand per weld. So 600 pounds. I still believe 600 pounds, believe it or not. I still believe 600 pounds. It's going to yield all hell, but I still believe 600 pounds. I mean, not yield. It's going to deflect like all hell, but I still believe 600 pounds. Way more than 15,000. Um, and as a sanity check, let's do M's. Let's go look at the. Let's actually take this load and see if what the actual deflection. Well, actually, first let's find the stress and see how much it's going to deflect. Okay. So we said sigma b test. Let's see, under maximum load allowed by welds, bending stress compute is. How do you continue a line in Python? I think you just backslash. Or actually, you might not even need to do that. We'll see. Bending stress in the. No, you do need to do it apparently. You want maximum. You want that in KSI. And then we convert that to, is it 0.2f? Oh, it doesn't take this gap well. Do we love Python yet? Well, that's a lot of stress. Do we believe that? I don't know if we believe that. The tube's going to fail way before the weld does. I don't know if I believe this. PL over 8. So it's MC over I, M times C over I, C, I think we calculated correctly. Print I. Millimeter cube to the fourth. Yep, that's right. All right, I guess it really is going to fail first. So what do, yeah, what's the maximum? I mean, is that right? I mean, that's not off by a little. That's off by an order of no, 2 orders of magnitude. That can't be right. Hmm. don't know what's going on with that. So PL over 8. PL over 8. And then bending stress is just making sure this isn't a syntax issue with Python. Um, so P times L times C divided by 8 times I. Yeah, I actually think that this one's wrong, but I don't know how to verify this. Kind of want to actually FEA this and see how wrong we are. So actually we'll do this one. So I'm going to export this in FEA. I'm going to run FEA to go just double check my calcs here. I'd also like to see how the stress distribution around the mounting features works. So we'll import the geometry. And we'll start to see what's going on. The loading for this is complex enough that we might want to use FEA anyways on the tabs, because these are complex loading. In other words, we're not just pulling on these tabs and distributing the stress at the base. We're actually creating a little cantilever. I'm sorry, we're creating a little moment. So let's get started on this. Do static, get our mesh. Solver, we're gonna fix both ends, like we talked about. Fixed our ends, and now we're gonna apply a load at the very center. And I don't know that I have a good place for that. So I'm gonna just put it, I don't know, here. Looks about center. Doesn't really matter. And we're gonna do load in X, no, Z. Load in Z. And what was our output load? 647. Let's apply it to both sides of the tube. So we'll say it's 650, well, 600 to 300 each way. So 300, save, and then we're going to do it on the other hole opposing it. So we get a better stress distribution. So that's effectively 600. but we're just distributing it more evenly over the over what we would consider a pseudo frame. And this is aluminum. We'll run this. Okay, so this will spit out the von Mises equivalent stress, which is roughly going to be equivalent to, well, it actually depends. So if the stress is at the outermost fiber, that will be our bending stress. If it's not at the outermost fiber, in other words, if it's at the center, we know something's wrong because the maximum stress is due to bending is at the outermost fibers. And when I say the outermost fiber, I mean the outside of the tube, so here. So that'll give us some feedback. In the meantime, let's double check our numbers here. So Pmax is Pmax, that makes sense, and that's 650 pounds. L is L might be wrong. Yeah, L's wrong. L sub beam. That's only gonna make the number go up. Yeah. Yeah, that's a bummer. C. Oh, this isn't a plate. C's not. C's the depth. C's the depth of the frame. So it what was it? T width? Yeah. But that isn't gonna help. We're still super high. What's going on here? More unit problems. I think again we have to do this ureg dot millimeter. Good, the number goes up. That's good. Yeah, let's see what this solution says. We actually should be looking for max principal stress, I think. That is lower than I thought. That's actually reasonable. 0.145, I thought that was it. So 255 times 0.14, yeah, 35 KSI. So the tube can take it. What the hell's going on? What did we do wrong in our calcs? All right, you know what? I've done something wrong here. And I don't know what it is, and this wasn't officially something I care about. Oh, be right back. This stream is officially sponsored by Spindrift. Grapeade. The best flavor. That is the one fact I can tell you on the stream. Grapeade is the best flavor. Spindrift. Apparently, that's the only thing I know because this is not. She ain't working. Okay, so I was wrong. I was approximating this all as the just the thickness of the plate here, and that's stupid. I forgot that I changes as well, so we have to recalculate I because but we do want to do a bending check on the tube anyways. So we do want to do a bending check on the tube. Problem is, it's going to be more difficult because we have to calculate the second moment of area for tube, and you know what? I do not have time for that right now because I want to find out what the pull strength of this thing is. We got the FEA. That's our answer for now. But we will come back and do this. This is not to say that we're never going to do it. Just that I want to be able to tell the team at FabWorks how much or worse, how much better or worse their framing system is than welding in terms of strength. So let's do that. So the maximum load is 650 pounds. With welding, let's find out what it is for a pull. This will actually be a quick FEA, I think. These are hard corners, so these stresses are going to be insane, but there's a trick you can do, which is this is not official engineering advice. I'm just saying this anecdotally. But for ductile materials, you actually don't have to look at the nodes right here. You can actually take some distance away from that and just instead ensure that you converge on an answer that makes sense in this area of the nodes of highest stress, which, as I said, this is not the official engineering for this right now. We are just doing some first order approximations, so that's good enough for now. So what we're going to do is we're going to find out how much can each one of these tabs take without exceeding yield. We're going to do that in FEA real quick. We can actually do a rough calc right now, and actually we should do a rough calc to see what we think it's going to be. So that is going to be, we'll draw this out. We'll draw this out. We're not out of space here. Actually, I should have some continuity here in terms of the way I thought about this. That's what arrows are for. Looks like that It's Always Sunny meme when he scribbles on the board and he's smoking and looks insane. Okay. So what were we doing? Okay, so this pull tab looks like so. There's 4 of them, 2 in this view. And this is the hidden line representing our tube wall. And that line, obviously, since we're doing that. So we can calculate the pull-out strength of this detail right now. And so first order, this is going to experience normal stress. That normal stress is going to be P for the load that we're applying divided by area. The area, if I take a cross section of this, call that cross section A, is going to look something like this, or to slice that tab. And then the tab is over here. And so this is my area. And I'm going to apply a force P to it. So we can do a quick check right now to get what this stress is going to be, and it's going to be length. Actually, we're gonna just come up with letters G, which is the distance from top to bottom, and a M. J. Nope, that's already running out of letters here. D from here to here. And so then that becomes the area is equal to D times G. Um, and so then we can substitute that in and we get this. And so this is going to give us our pull-out stress, which will essentially give it our pull-out force. Actually, let's solve just directly for the force. So we'll pull these over and we'll get the pull-out force capable of the material and the geometry. So that becomes the stress times D times G, and that equals our pull-out force. Isn't that fun? So let's, and to summarize what's going on here, normal stress is P over A. We're only calculating the normal stress right now. That's happening at these tabs right here. We're going to assume that the tube is stronger because it has more area around it to distribute the load. And the area is equal to D times G, and we're going to apply load P on this cross section and pull on it, like so. So we have sigma dg. Sigma, so it's going to be P max tab is equal to sigma, what do we call it? Do we just call it sigma? Might have to learn how to collapse tabs here. Sigma yield times D, which was, we're going to measure that right now. D is 1.6. That makes sense. It's actually H, I think. Oh, yeah, it was H. It's just the thickness of the material. And then the tab height is going to be that measured to here, which is the z-axis, and that is 7.13. And then we should be able to get an answer right out of this. E max tab, max tab. So again, we get this stupid pint issue. 820 pounds. Holy moly. Is that real? That's way more. Wait, no, that's pull force. That's pull force just in this region. And actually, that kind of makes sense. I believe that. And I bet you if we go run the FEA, we'll be surprised by the fact that that's roughly true. Let's make a run 2 real quick. What are you doing? Don't run the sim. No. That was my fault. What are we changing here? Boundary conditions, that stays. Forces change. So we're going to apply, we can roughly just for the check on, just for the check on normal loading, we're not looking into bending yet. The eccentric loading of the engagement of that tab. So it's 821. No, I'm not logging in the stream on the stream. So we're not going to be able to do this. Let me just see if I can get out real quick and fix this. Yeah, that fixed it. Good. So A21, pound force in Y, actually. We're going to see if we get to that yield value. Okay, let that run. The cool thing about this is that's only one tab. We actually have 4 of them, so this is much more skookum than we thought. So we can actually count, we can actually, hmm, how can we quickly calculate this? What we can do is um, we can calculate the moment we have to resolve between these 2 sets of tabs. It's essentially the distance from the center of the tab here and here, and then set that equal to the moment like we did before. And that'll help us get a really quick answer. And what we're doing here is we're trying to find out we're setting up the same system of equations here, except we're replacing the weld with, we're replacing it with the strength of the tab. Which is kind of nice the way we thought about this. So we're working back from this equation. We're actually working back from this equation here. Yeah. So R1 and R2. Yeah, okay. Here we go. So pull this over. Actually, before we keep going, let's look at the results on this sim. It works. I mean, it's crazy, but it works. It's only 265 times 0.14. Yeah, 37 KSI. So these tabs can take. Don't you love it when FEA matches calculation? Is that not the best? So yeah, this works. It could take 800 pounds. That's crazy. Now, the problem is that we have less distance to decouple moment over. So we're going to need that load, but let's see. Um, let's just write it out. So originally we had this. Four and five. We want these 2 equations. So we actually have this value now. So we can actually just say we can actually replace R1 and R2 with Pmax. One second. Okay, so we we're replacing R1, R2 with Pmax. which is this. So we can, I think we can quickly just plug this in now. So wait, is that right? What are we forgetting here? We shouldn't call this Bmax. That's going to confuse us. Call this P tab or R tab. Yeah, R tab. R T for tab. And then we're going to rewrite. Actually, we're just going to pull this over. Change this. And then I double check that RT made sense here. Yeah, reaction forces there. W changes as well because our distance between them changed. So we'll call this RT for tab. I'm sorry, WT. And WT is equal to this distance, the distance between these two tabs. So I'll find center here. And then just get the measurement there. That's 22.16. That's from CAD. So let's write all this out. And actually, let's just one more time double check. This is L, is that the length of the weld? No, that's the length of the frame, right? L beam? I think that's right. Yeah, that's L beam. Okay. Maximum load capable of the tab details. So it's E max tab is equal to 4 times R sub t times W sub t divided by length of the beam, which we already have length of the beam. But we do have to declare R sub t and W sub t. So R sub t, what is R sub t? That is the value that we came up with here, P max tab. So actually we'll call R sub t. That's still calcs, we're good. That's already declared, so we can get rid of that. And then finally, we input the value from CAD. And let's find out now. Actually, so this is per tab. We actually want, no, this is right. This is right, I think. Let's see if this spits out the answer. Let's copy this. The maximum load the frame can withstand with tabs is P max tab. Oh, well, that's less impressive. So 81 pounds. You know why that is, though, right? It's because you have to decouple the moment. You have to decouple the moment over this tiny little distance from here to here, versus you had the ability to do it from here to here, which makes this way, way weaker for the tabs. And so to prove that, if I come back here and substitute W sub t for the width of the frame, that number goes up. Yeah. All right. So what is the so what's the difference? So um, so the ratio WT, in other words, ratio of weld to tab, is equal to P max divided by P max tab. Print ratio. So it's the welds are 8 times stronger. Ta-da. That's the answer. I haven't double checked it, um, but it's a first shot. And the FEA is correlating, so I kind of trust the answer. So in other words, if you were capable, if you tested this frame, put a load here, and it broke when you welded it, and you welded it and it broke at 1,000 pounds, it would be an eighth of that for the tabs before it would break. So it would fail at 125 pounds. Now the good news is I don't know that it's not usable. 80 pounds, you know, could be better, but that's still usable-ish, and I think there's room for optimization here. And that was the point. That was the goal of the stream today. So I'm going to end it there. And if you catch any issues, please add me. And we'll come back next time and see if we can close this calculation sheet out, make it usable or useful. And I'll actually, before I leave, I will commit this to the GitHub. Next stream will be probably tomorrow, if not Monday. So I'm going to develop a regular schedule for these. I think I want to do as early as possible in the afternoon PST, but that's a challenge right now for me, given my current schedule. So I'm shooting for 2 p.m. every weekday, and then essentially bonus streams when I can on Saturday and Sunday. Um, but I have to work the schedule out. So right now it's pretty regularly early afternoons on weekdays. PST, so Pacific time. But I'm gonna do a post on when these streams are gonna become regular. In the meantime, if you miss them, they are on YouTube. So these are now currently being streamed to my channel on YouTube. And I will post a link to that actually, real quick. So you can find these on my YouTubes. They automatically, so they stream here. I mean, they stream to YouTube if you prefer YouTube as a platform. But the other benefit is they get saved automatically there. So I personally prefer rewatching videos on YouTube. So like and subscribe. It's the first time I've gotten to say that. Okay, calcs are on the GitHub. Take a look. If you find an issue, let me know, and I will see you next time.